going to factor the denominator. So this is x, let me see, two numbers add up to -1, product -2. It has to be x minus 1 and 2. Let me see, it's x plus 1 times x minus 2, correct? Okay, so that is the denominator. Now, the first thing I'm going to find the asymptotes. So I'm going to say the degree of the numerator is less than the degree of the denominator. And when that happens, you know that the equation of the horizontal asymptote is going to be the x-axis, right? So I'm going to say y equals 0, which is the equation of the x-axis. That is the horizontal asymptote. And for the vertical asymptote, by setting the denominator equal to 0, I believe we will end up with two roots for the denominator. So x equals 2 and x equals -1 are the two vertical asymptotes for this function. So we don't have any slant asymptote. I'm going to mention it. No slant asymptote, because slant asymptotes, as you know, they appear when the degree of the numerator is 1 more than the degree of the denominator, but that's not the case here. So no slant asymptote, two vertical asymptotes, one horizontal asymptote for this given function. That's part A, finding the asymptotes. Part B, we want to draw these asymptotes first of all. So I'm going to draw the vertical lines. So this is one of the vertical asymptotes, and this is the other one. Okay, and I can label them. This is x equals what? X equals -1. This one is x equals 2. These are the two vertical asymptotes. And we do have the horizontal asymptote, which is nothing but the x-axis. So if I label this, it's going to be y equals 0. So these are the three asymptotes. Now, I just want to know the behavior of the graph at a neighborhood or vicinity of the vertical asymptotes. And for this purpose, I have to use one-sided limits. So I'm going to say limit of the function when x approaches 2 from right-hand side. I'm going to try to find this limit. I want to know what happens to the value of y if x approaches 2 from right-hand side. Let's say x is, let's say 2.1 or 2.001 or something close to 2, but more than 2. So if that's the case, then 2.1, let's say minus 2, would be positive, and 2.1 plus 1 is positive, the numerator is positive, so everything is positive. The denominator is getting closer and closer to 0 because x is approaching 2, so you know that number divided by 0 is infinity, and the result of the result of the limit would be, of course, infinity, because this whole fraction explodes when the denominator becomes extremely close to 0. But the type of the sign of the infinity is what we care here, what we are interested in. And as I said, everything was positive here, so the sign is positive infinity, meaning that on the right-hand side of the vertical asymptote, we have our graph going towards positive infinity. So this is the behavior of the graph on the right-hand side. And if I take the limit of the same function, but this time x approaches 2 from left-hand side, this time we are picking a value for x that is close to 2, but it's less than 2, such as 1.999. If x is 1.999, this factor here will be negative, but very small, very close to 0. This factor will be positive. The numerator is positive. The whole fraction will become negative clearly. And it will be negative, of course, infinity, obviously, because the denominator is getting very close to 0. Imagine x is 1.999, or even 1.99999 forever minus 2. That would be a very small negative number close to 0. And that is the reason why we end up with negative infinity. And this tells us that the behavior of the graph at the vicinity of its vertical asymptote x equals 2 would be at the bottom right here somewhere at negative infinity. So the graph behaves like this. Similarly, for the other asymptotes, we have to repeat this, unfortunately, because we have two vertical asymptotes. This time x approaches -1 from the right-hand side, and we are going to find this limit, as well as x approaches -1 from left-hand side. We're going to find this other limit. So I have to write these things very fast because of the time constraint I have in these video lectures. If x approaches -1 from the right-hand side, let's say it's -0.99, you plug in 80.99, this would be positive, this would be negative. So the whole thing would go negative infinity on the right-hand side of x equals -1, which is the vertical asymptote. But this other one, if x approaches -1, so let me quickly do this part of the graph. That's what is happening on the right-hand side of the vertical asymptote. For this one, if x approaches -1 from left-hand side, let's say it's -1.1. So -1.1 would make this negative, a very negative, a very small negative number. And this would be negative. So negative times negative is positive. So the numerator is positive, the denominator is positive. So the whole thing will become positive infinity, of course, as per this analysis. So this means that on the left-hand side of the vertical asymptote x equals -1, the graph should behave like this at a vicinity of its vertical asymptote. In section 3.4 of the textbook, there's also a good example similar to this, which you can, of course, read it. And I assume and I trust that you are actually reading the textbook not only once, not only twice. This is like a good chance for you to become an independent learner. Okay. All right. So we've got the behavior of the graph. Now, other things we can do in order to sketch this graph is taking care of the x and y intercepts. So I'm going to set y equal to 0, and I end up with this function, which clearly is never ever equal to 0 because the numerator is 1. What do you expect? 1 cannot be 0. And the message is that there is no x-intercept. That's the message. It wasn't your fault that y cannot be equal to 0 because the numerator is 1. But if you set x equal to 0 to find the y-intercept this time, then you end up with 1 over 0 minus 2, and then 0 plus 1, and that gives you -1/2 or -0.5, which is actually your x-intercept. So this means that the graph must intersect the x-axis at -0.5. Am I right? No, I am not right. This was to set x, this was the y-intercept. I mentioned x-intercept by mistake. X-intercept, we already said it that it doesn't exist. I apologize because of the rushing I'm doing. So y-intercept is -0.5, and that is right here. So this is the y-intercept. It's about -1.5. Okay, so we know that the graph behaves the way it is shown so far at the vicinity of its vertical asymptotes, and also we know that it intersects the y-axis at -1/2, and also we know that it does not intersect the x-axis or its horizontal asymptote at all. Okay, so let me see what else I can find out about this function. I'm going to take the derivative, if you don't mind. So the derivative of this rational function would be u prime is 0 minus b prime u, so -2x plus 1 over the denominator squared. Okay, so that is the first derivative. You can spend 5 minutes taking the derivative separately. You can always stop the videos. And then I'm going to set this derivative equal to 0, and I get an x value of 1/2. This means that this is a critical number of the function. And in order to find out if this is a maximum point or minimum point, I can either use first derivative test or second derivative test. I'm going to use a first derivative test this time. you know, I go 1/2, and I have the numerator, -2x plus 1. I have the denominator, which has an exponent of 2, and then I have y prime and y clearly. So if I subdivide my set of real numbers into different subintervals, -2x plus 1, which is the numerator of y prime, is 0 at 1/2. We just found the critical number. So to the right would be negative, to the left would be positive, obviously. And this expression is always positive, so we're going to have always positive. And it is 0 actually at -1 and 2. I could have included it in my chart, and I'm going to do that actually. -1 and 2. So I'm going to put the 2 here. Oh, this is blue. I'm going to put the 2 here, and I'm going to put -1 here. Okay, so I'm making the chart to include the asymptotes as well. And the denominator, as we said, is 0 at -1 and at 2, because these are the roots of the denominator, obviously. So plus here, minus there. And as I said, because the denominator is always squared for the y prime, so it's going to be always positive no matter what. Now, when you divide the numerator by the denominator, you get positive, positive, negative, negative. And this 1/2 is the root of y prime. Y prime would be infinity or undefined at 2 and -1. So I'm going to include them in my chart. And looking at the sign of y prime, I can tell that the graph is increasing, and then decreasing and decreasing. So according to the first derivative test, y prime is 0, and it has changed its sign. So that means that this is actually a local maximum point happening at x equals 1/2. So x equals 1/2. If I plug in 1/2 in the equation, what is f at 1/2? It would be something probably around the 9/4 or 4/9. Let me see. I had it. I had written it somewhere. 4/9, -4/9. You can do the calculation by using a calculator. So 1/2 is here. -4/9 is somewhere here. So apparently the graph has a local maximum point over there, and the graph looks like this. I'm going to complete the graph now. It has sort of a parabola-shaped kind of graph in the middle. On the right-hand side, it's going to go like this. It becomes closer to the horizontal asymptote, but it doesn't touch it because the x-intercept didn't exist, if you recall. And this part, of course, is again similar. It goes like that, gets closer. So this is the general sketch of the function y equals 1/x² minus x minus 2. So that's how the graph looks like. And we see that the chart information matches with the graph. Like, I can say that the graph is increasing over the interval from -infinity all the way up to -1. And then from -1, again, it is increasing up to 1/2. And I can say that it is decreasing wherever y prime is negative. I mean, from 1/2 up to 2, and then once again from 2 towards positive infinity, it's decreasing. So I did find intervals of increase and intervals of decrease. I did find the local maximum point, which was here. So here, this is actually our local max point. The coordinates of local max is just, let's say this is point A. So point A has coordinates of 1/2, -4/9, and this is our local maximum point. We also examined the behavior of the graph at the neighborhood of its vertical asymptotes. And I think this is good enough for now for this section in terms of finding asymptotes, equations of asymptotes, sketching the graph, finding local max min, and putting basically everything together to draw the graph of this rational function. Okay, so wait for more lectures to come. Thank you.